Okay, so we're interested now in drawing Lewis structures. And a lot of what chemistry is about is appreciating the shape on the molecular level of molecules and the special properties that come with certain shapes. And before we can start talking shapes and geometries, we have to be able to visualize the molecules. And so Lewis structures, also known as electron dot structures by some, are really very simple. For any atom or molecule, a Lewis structure is nothing more than a symbol, the atomic symbol for each atom in the structure, and all of the valence electrons for each atom, not all the electrons, but all the valence or reactive electrons, drawn as little dots in the structure, or as lines, we will see. Now, we'll start off with something really simple like an atom. And let's say we're going to talk about nitrogen, a group 5 atom. Well, if it's a group 5 atom, that's for a good reason. It has 5 valence electrons. So I would represent the Lewis structure for nitrogen by simply putting the symbol N and then drawing 5 dots around the 4 sides of the atom. And yes, we have a pair up here. But in general, I'm looking at a nitrogen and 5 valence electrons. And this is how we represent nitrogen. Now, if we get into molecules with whole groups of atoms, it's going to be a lot easier to do this if we have some rules. So for the first rule, what we're going to do is calculate the total number of valence electrons that we're going to need in the structure for it to be correct. And so let's have a couple of examples to play with at once. Something simple, like, say, ammonia, and something less obvious, like, say, nitrate or carbonate ions. So this first rule simply tells me I'm going to calculate how many electrons should be in my structure. Now, nitrogen is, of course, a group 5 atom, and I have 1 nitrogen atom, so it should bring to the structure 5 valence electrons. And we have 3 hydrogen atoms, each in group 1, so they should bring 3 more. If this structure is to be drawn correctly, there better be 8 electrons in the final structure. Now, if you have an ion, because we're going to calculate the number of electrons and adjust if it's an ion, nitrogen, again, brings 5 electrons to the structure. Oxygen, all 3 of them, would each bring 6 as a group 6 atom. And lastly, the whole group of atoms is an anion, has a negative charge, because this group of atoms has an additional electron. And of course, when atoms gain and lose electrons, they don't lose their inner electrons down in the core of the atom. They gain and lose their outermost, or reactive, otherwise called valence electrons. So this group of atoms has gained an additional electron and would have 24. Lastly, if we're calculating for carbonate ion, 1 carbon atom would bring 4. 3 oxygen atoms would bring 6 each for 18. And we've gained 2 additional electrons in this structure, so this will also have 24 valence electrons. So step 1 is simply looking up which groups atoms are in. That's how many valence electrons they should have. And then adjusting the number upward or downward for cations or anions. So for the second rule, we need to pick an atom that's going to be in the center of the structure. Now this works especially for simple inorganic molecules like the typical first-year student would be drawing. This won't work for the more complex organic molecules containing lots of carbon, hydrogen, and other functional groups. But for the simple inorganic molecules, the central atom will typically be the atom of greatest valence. Now remember, valence means reactivity, and the valence of the atom is determined by how many more electrons it needs to gain an octet. So say a group 5 atom like nitrogen with 5 valence electrons will have a valence or reactivity of 3. It's going to attempt to achieve 3 more electrons. An atom like oxygen in group 6 would have a valence of 2. It's trying to achieve 2 more. And for most structures, The central atom will be the atom of greatest valence, which makes sense. The atom that needs to react the most with other atoms should be at the center of all the atoms. Now, for more advanced students, the central atom is invariably the atom of lowest electronegativity, but if you're a first-year student, don't necessarily worry about that. Now, exceptions to the rule, if you're going to use the valence rule, is that if the molecule contains a noble gas, the noble gas will always be the central atom. And if the molecule is an oxoanion, like these two right here, then automatically you should know that the non-oxygen atom will be the central atom. So, if I'm going to pick a central atom in this structure, since nitrogen has the greatest valence, 3 versus 1, remember hydrogen can only gain one more electron because it's in the first period, and its valence level is the first energy level, and the first energy level has only an s orbital and therefore can only hold 2 electrons. So hydrogen achieves a noble gas configuration like helium. It gains one more electron to have 2. So the central atom here is going to be nitrogen. Central atom here, because it's an oxoanion, will be nitrogen. Central atom here, because it's an oxoanion, will be carbon. Now, the next rule, we want to arrange the other atoms around the central atom in this step, and we want to join them to the central atom by one shared pair, or a covalent pair as it's called, of electrons. So in ammonia, NH3, we want to arrange the other 3 hydrogen atoms around the atom, central, and we represent a shared pair of electrons by a line. Remember, a line represents a shared pair of electrons. It is also acceptable to put a pair of dots in between. But in most structures, to save time, a shared pair is represented by a line. Now, the same thing for nitrate, only in this case we have 3 oxygens arranged around our nitrogen and a shared pair between each. And in carbonate, we also had 3 oxygens surrounding the central carbon, shared pair each. So pretty simple. Arrange the other atoms and basically create a force of attraction between them by sharing a pair of electrons. So for rule 4, we are now going to add lone pairs of electrons. Now, these are pairs of dots, represented, of course, just by dots. We're going to add lone pairs to each atom so that each atom has its valence octet, so to speak. Now, please note this rule does not apply to 3 atoms, namely hydrogen, which never achieves an octet, at best a duet, 2 valence electrons, beryllium, which is in group 2 and only has 2 electrons to share, so it rarely ends up with more than 4 in most structures, or boron in group 3, which only has 3 to share covalently, and in sharing covalently at most it usually ends up with 6. So we're going to avoid this step for all of those atoms. Now in this case, 3 of the atoms are hydrogen, so I just slap a lone pair on the nitrogen and I have achieved an octet for the nitrogen. Here, all of the atoms require lone pairs to achieve octets. And all I'm doing really is covering up all 4 sides of the atom with electrons. And let's not forget that shared pairs are represented by lines. So everyone has their octet. Same thing here, everyone needs an octet. And now for the only step that's really important, and the only step where you have to be careful and think. We are now going to count the total number of electrons in the structure and compare it to the number we calculated in step 1 and adjust the number of electrons if necessary. So in our first example, we have 2, 4, 6, 8 electrons. And if you remember from our initial calculations, we wanted 8 in the structure. So this structure is fine. I'm going to leave it as is, no adjustment necessary. However, on this structure, we have 8, 8, 8, and 2 more electrons for a total of 26 electrons. And 26 electrons is 2 more than we calculated. We wanted 24. Same thing in this molecule. 8, 8, 8, and 2 more is 26. And we also wanted 24 in these structures. So if we need to adjust downward, namely decrease the number of electrons, it's easy to do. There's a method. It's almost rhythmic. What you do is take a lone pair of electrons, turn it into a shared pair with the central atom, and then eliminate a lone pair on the central atom. What do I mean? I mean this. I'm going to take a lone pair right here and eliminate it, but I'm not getting rid of it. Instead, I am going to share it with the central atom, if my pen will let me, which it's not. There we go. And of course, in so doing, this atom acquires 2 more electrons in its valence shell. And so that eliminates the need for this pair of electrons, and it can still have 8 electrons total, which is what all atoms are attempting to achieve, a valence octet. And so when I eliminate a pair, I still have an octet, an octet, an octet, and an octet around all 4 atoms, but I'm down to 24 electrons. And this would be the correct structure. However, if it's an ion, and nitrate is, you must enclose the structure in square brackets and put the charge outside those brackets, and you're done. Now, the same situation was true on carbonate. We were 2 electrons too large, so we need to eliminate a pair. And the way to do that is to take a pair, share it, and get rid of a pair. And I should have gotten rid of both there. And it doesn't want to erase one of them. So, in any event, had that other electron decided to go away, and I'll make it go away by actually drawing the square brackets for my ion on top of it. -2 charge out, we have the correct structure for a carbonate ion. Now, if you're a more advanced student, an AP student, say, or honors student, we need to play further with these structures. We need to explore what's called resonance, and we would also have to calculate what are called formal charges on each atom. But for most first-year students, this is a sufficient way to draw a molecule. Now, let's do another one where we actually have too few electrons when we're done. And as an example, I'm going to choose, say, krypton difluoride. Now, if I choose a central, well, first, before I do that, let's make our calculation. Being a group 8 atom, krypton should have 8 valence electrons. And my 2 fluorines, halogens, should have 7 each. The structure should have 22 valence electrons, or it's incorrect. Now, because there's a noble gas in the structure, I immediately select it as a central atom. I covalently bond once the other 2 atoms, and I give everybody octets. And when you stand back and count up, you'll notice that you have 8, 8, and 4, 20 electrons. We needed 22. We need 2 more electrons. And there's a way to figure out where they go. And that is, somebody in the structure is missing 2 electrons. And here's how to tell. If I look at this fluorine atom right here, I know that half of these 2 shared electrons came from the fluorine atom. That's 1. And that it has 6 other valence electrons for a total of 7. And because fluorine's in group 7, it should have 7 valence electrons. Same thing's true of this fluorine. But the krypton's another story. The krypton gave 1, 2 of each of these shared electrons to the 2 fluorines, and it has 4 more on it. It has 6 valence electrons. But you see, krypton's in group 8. It should have 8. And so it's the one missing the additional 2 electrons. And you add them as a pair. Don't split them up. And you have the correct structure of krypton difluoride. Now also, one other detail, krypton is the only atom here that could have what's called an expanded octet, more than 8, because its valence level is the 4th energy level, and there are 4 electron sublevels that can accommodate a total of 32 electrons. Not the case with fluorine in period 2. It can only have 8 valence electrons, no expanded octet.